Another math talk. Today we have our special guest Soumendu sir from ISI Kolkata. He did his BStat and MStat from ISI Kolkata itself and PhD from UC Berkeley under Preet JPK. And he is currently a professor at ISI Kolkata. Over to you, sir.
Thank you, Vikram, for the invitation. Okay, let me try to share my screen. Yeah, is my screen visible?
Yes, sir.
Okay. Okay, so yeah, okay. So I'm going to talk about generalization of the coupon collector problem that you are perhaps already familiar with. So this is a work based on joint work with Shiva Atreya and Satyaki Mukherjee. So, okay, let me begin with let me recapitulate the coupon collector problem, which you are probably already familiar with, but nonetheless, let me do it again. So, suppose you have a bunch of coupons which are numbered, which I'll denote by these circles, and I'll number them by 1 to n. Okay? And suppose you have a person who is after this coupon, he wants to collect all these coupons. Okay? So at each round, he will draw one of these coupons at random. So we're interested in the time it takes to collect all the coupons. Okay? So you have n distinct coupons. You want to know on an average how long does it take to collect all these coupons. Okay? I'll denote this time by t. Of course, t is a random variable. Now, yeah, so this is a elementary exercise to compute the expectation of t. Yeah, if you have any question, feel free to stop me anytime. Okay. Okay. So t is the time to collect all the coupons. Okay. And suppose you want to calculate expectation of t. So how do you go about it? Well, okay. To collect the first coupon, you need one round definitely. After that, let's try to see how long do you need on an average to collect the next new coupon. Well, you have collected one coupon already. So in the next trial, the probability that you will draw a new coupon is basically n minus 1 over n. Right? Same for this first coupon, you can draw any one and that will be a new coupon. Right? So it is like a geometric trial. So you toss a coin with this success probability, and when you see a new coupon, you have got your second new coupon. Right? So you all know that the mean of a geometric is 1 over p. So the time to collect the next coupon on an average is n by n minus 1. And similarly, if you go for the next new coupon, the probability of collecting it around in a round is n minus 2 over n. So you get this n minus 2 over n by n minus 2 all the way up to n. Right? So here you basically get the harmonic number which behaves like log n. So this is n log n. plus 1 plus the log 1. So basically, you take you need n log n time to collect all the coupons. So that's the basic coupon collector. Okay, I have a question for you. Suppose instead of drawing one coupon at random, at each round I draw, let's say, R coupons at random without replacement. Then what do you think? How long will it take on an average? Okay, that is R distinct coupons each round. So then how long would it take? What would be your guess?
So, is this drawing without replacement or with replacement?
Without replacement. So you basically at each round you draw R distinct coupons. And then you draw another R distinct coupons and so on.
Then it should be just n by r.
Yeah, it should be whatever it was before by R, right?
Yeah.
So okay, this would be a fun problem for you. Problem. Show that in this case, the expected time to collect all the coupons would be basically n log n over R. Okay, so now I will talk about. So there has been various generalization people have considered previously. I will consider a particular type of generalization. So again, I have a bunch of distinct coupons, again numbered 1 to n. So at each round, I will draw R coupons at random, like this. So at each round, I will draw R coupons without replacement, and I will collect. So I'll look at all possible occurrences of S subsets of coupons. Okay, what do I mean by that? Well, imagine that any S subset, okay, so S is something less than or equal to R, bigger than or equal to 1. So any S subset of this 1 to n, I will call that a super coupon. Super coupon. Okay, so at each round, I will be drawing R coupons without replacement, where R is bigger than or equal to S, and I will look at all the possible super coupons I have collected. I will mark those things as collected. So if I draw R coupons without replacement, there are R choose S subsets, R choose as many S subsets. So I will mark all of them together as all of them as collected. Okay. So in particular, if S is 2, then you are looking to collect all possible pairs of coupons. And at each round, I am drawing R coupons. So I will at each round I will be seeing R choose too many uh, super coupons. Again, the goal is to collect all the super coupons. So I want to collect all possible n choose S many super coupons. T will denote the time to collect. So this is the problem I want to consider in this. So this is a generalization of the coupon collector problem. Obviously, for instance, if S is one, uh, then basically I'm talking about this problem. I'm just collecting regular coupons, and I should take on an average into n log n over r time to collect them. So S is equal to 1. It's the usual coupon collector where you draw r coupons at random. R equal to S is also another variant. The coupon collector. Do you see why?
Yeah, there is only one coupon to collect.
Exactly.
Yeah, that's
So
the basic one.
exactly. So basically, it's you can call it the regular super coupon collector problem, right? At each round, we see exactly one super coupon. So R equal to S is also coupon collector. So in the R equal to S case, then we know the answer because based on our previous calculation. So it's going to be n choose R log n choose R times 1 plus this log. And for S equal to 1, again we know it's in log n by R. So what do you think is the answer when S is strictly between 1 and R? Then what is the answer? So before going there, let us think about a simpler problem. Uh, Suppose at each round, the, the problem here is that at each round I am drawing R many coupons and marking all the S subsets of those R coupons as collected. So there is a constraint going on here. The the R choose as many super coupons that I collect at each round, these super coupons that I collect at each round, they form a R subset. Their union is a R subset. So these are not arbitrary super coupons. So at each round I collect super coupons who sort of maintain a certain constant. So their union is an R subset. Okay? Suppose I get rid of this constant. Suppose I just had at each round I just collect R choose S many super coupons. Okay? Any super coupon. So I get rid of this constant that their union is an R subset. Okay? Then what would be the answer? So at each round, I'm basically collecting arbitrary R choose S many super coupons. So see, then this is nothing but this problem, right? I'm just at each round, I'm drawing R choose S many super coupons without replacement, and I want to collect all the super coupons. So I know what the answer will be. The answer will be again in choose R, rather in choose S, because these are the total number of this is the total number of super coupons log into this divided by r choose this. This is basically this problem. Okay, so if I get rid of this constraint that these r choose this super coupons, their union is an r subset, then I know the answer. Well, then suppose I have this constraint. It turns out the answer is the same. So even if you have this constraint that the union of these sets is an R subset, then also this is the answer. But it turns out it is much more difficult to prove because of this constraint here. So I'd like to discuss the proof of this fact. Okay, so yeah, so we won't be able to calculate the expectation exactly, unlike the coupon collector problem. We'll be content with proving this asymptotic state. So how do we prove it? Well, the proof will be based on what is called the moment method. Okay? In fact, proved by only the first two moments of a certain random variable. You need to compute the first two moments of a certain random. Well, okay. So let us begin with this expression, so which you are all familiar with. So expectation of t is basically the sum of these tail probabilities, probability t bigger than k. So we'll relate this to a certain count random variable. So see, if I define a random variable nk to be the number of coupons, number of super coupons, which are not collected by round k. Then what can we say about this probability in terms of nk? I want to express this in terms of nk. Nk is a count variable, so it will be easier to handle.
NK positive.
Nk positive, right? Exactly. If you haven't uh, really uh, seen all the coupons, then by time k there will be at least one coupon that you have not seen. So nk must be positive. Okay, so this is the main idea. So we will try to find suitable upper and lower bounds on this. Okay. So the main two ingredients will be, so for upper bound, we'll be using the first moment method. For the lower bound, we'll use the second moment method. So, okay, let us try to find an upper bound. So probability nk bigger than 0. Nk is a non-negative integer valued random variable. So this is probability nk bigger than or equal to 1. And now we can apply Markov's inequality to say that this is less than or equal to expectation of n. So we need to calculate expectation of n. So let us do that. So what is expectation of nk? So, so nk, recall, is the number of super coupons not collected by time. So we'll basically write it as a sum of indicators. So this is when when you can do when you can really write a count as a sum of indicators. That's when the first and second movement methods are really powerful. In this case also you can do something like that. So we sum over all possible subset, all possible super coupons. Okay. And we'll put an indicator. The indicator says whether that particular coupon S has been seen by time k or not. Okay. So I'll write it as ISK. This indicator says whether one super coupon S we have a bunch of indicators. They are of course not independent; they are correlated. But for calculating the expectation, there is not much to do. It's linear, so expectation of nk is going to be just and these are all exchangeable. I mean, there is no real difference between S and S prime, so we can just write this. Okay. So for brevity, I will write M to be n choose S, and this is M times. So let us compute this guy. So basically, you want to see whether you have collected this particular super coupon S by round k or not. So if you haven't collected it, so this is a probability that you haven't collected this. Uh, but these rounds are all independent. So this should be some probability to the power k. So you can immediately see that what is the probability of not seeing this super coupon in one round. So you can write it as the probability of seeing this super coupon in one round. And if you see this particular super coupon, that means that you have already seen these S coupons, but you have R coupons are done. So basically, you have to choose the rest of the things, right? So you just get in choose S. This is the probability that you don't see this particular coupon at a single round. I have k rounds, so I just and these are independent, so I just take the power of k. So for brevity, I will also denote this number by theta, and we will note that theta is n minus s choose r minus s by r. We will note that theta has the following asymptotics. Uh, Factorial and factorials. Okay, so that's my expectation of in K. Okay, so let us so using this, let us compute the proof of the upper bound that the expectation of T is really at most this. The expectation of T, as we have seen, is sum of expectation of nk or expectation of or rather sum of probability nk bigger than 0, and then by the first moment by Markov's inequality, this is less than or equal to expectation of. Okay, I mean, let me keep it like this here. Okay, so how do we use this to prove that expectation of t is at most this? Okay, so what we are going to do is, these are all probabilities. These numbers p, n, k bigger than 0, these are all probabilities. So uh, these are at most 1. So here's the intuition. You see, if k is really small, then what can you say about probability nk bigger than 0 if k is small?
Be almost 1.
Should be almost 1, right? So for small k, all of these terms will be basically contributing 1. So, so we'll be very hopeful and break this series into two parts. One is up to some number m, and that number m would be exactly this, up to some threshold m. And after that, we have this tail. We will try to show that this tail is negligible after a suitable choice of m. And up to m, these are basically contributing 1. So this first term will be essentially m. Okay? Very good. So let's see. So what should I take as my m? I will exactly take this as my m. Okay? I'm bit quite hopeful that it will work out. So let's see if it works out or not. So yeah, we just saw that probability nk bigger than 0 is at most expectation nk, and that is m times 1 minus theta power k. So if you look at this tails sum here, this is at most you have a geometric series. Basically, the only series that we know how to sum. Uh, yeah. So so basically, we get m times 1 minus theta power m by theta. Right? Okay. So so now it's almost there. We just see what this term is, what this estimate gives us. We'll take m to be the number that we want it to be. So basically, this object. N choose is log n choose s. Let's say let's put a. I think I was ceiling. This is also, I think we can write it as n power s log n power s, so that will give you s. Basically get n power s log n by s minus 1 factorial. So I'll take this as my m. If I do that, then I see that this is less than or equal to. Here I'll bound all of these probabilities by 1, so I get m plus this tail. So m plus m into 1 minus theta power m over theta. So I'll try to show that this is negligible compared to this m. We see that m is of the order of n to the power s log n. So if we just show that this second term is smaller than that in magnitude, we are good. So let's see. Okay, so yeah, so theta we already saw is like s factorial r to the s by into the s. Okay, so what is 1 minus theta power m? 1 minus s factorial r to the s over into the s. M is basically n to the power is log n by s minus 1 factorial r to the s. Right? So this is essentially e power minus uh, s factorial. So this times this. So s factorial
It's factorial log n.
log n divided by this, right? Basically that, right?
Yeah.
So you basically get e power minus s log n, which is nothing but n power minus s. Okay, so this is just n power minus s. Okay, so 1 minus theta to the n uh, is of the order of n power minus s. So let us plug this
It is
in
of the
here.
same order as theta itself.
It is the same order as theta itself, exactly. So that's it. So therefore, these two get cancelled in order, right? And you just get n to z, which is basically order of n to the power s. Okay, is everyone happy? So as you said, a 1 minus theta power m is has the same order as theta itself. So these two get cancelled in order, and you just have this n choose s, which is just order of n power s. And that is good enough because I know that my m is larger than this. M is n to the power s log n. So I have we will. So this proves the upper bound. We have just proved that expectation of t is less than or equal to yeah n power into this log and plus this plus something which is smaller order. So I'll just combine everything together and write. Okay, so that gives you the proof of the upper bound. Let us prove the lower bound, which is more interesting. The lower bound, we want to prove something like this again, but with this direction. So the starting point is again that inequality that we had earlier. So that representation. So expectation of t is summation a bigger than or equal to 0 probability nk bigger than 0. Yeah. So in the upper bound, what we sort of observe is that for small k, these probabilities are almost close to 1. So for the lower bound, we need to quantify how close to 1 these are. Yeah. Okay. So let's do that. Since we yeah, so basically the idea is the first m terms basically contribute and give you the main term. We'll drop the rest of the terms. So we just write this is bigger than or equal to k up to m probability nk bigger than. We'll just drop the rest of the terms because I'm interested in the lower bound. And then I want to lower bound these guys. Probability nk bigger than. Very good. So now comes the second moment method. So, so for any non-negative random variable, you can prove that probability x bigger than 0 is at least expectation of x whole squared divided by expectation of x. If you haven't seen this, this is an exercise. Proves like you prove the Chebyshev inequality. This is true for any non-negative random variable. This is true. We have this inequality. Okay, so let us use that to lower bound this guy. So this expectation in case squared divided by expectation of n. Now, so we need to calculate expectation of nk squared. So for simplicity, I will write it. I'll see. I mean, nk is like a sum of indicators. So yeah, we'll have to estimate this expectation of nk squared. I mean, I can write it like this, or another form which might be more helpful here is I just express this in terms of the variance of nk. So if I do that, then this is just expectation of nk squared, variance of nk plus expectation of nk squared. So this is 1 by 1 plus expectation, or 1 plus variance of nk over expectation of nk. You see, our goal is to show that the intuition is tight. So we want to show that this guy is actually close to 1. This is, of course, so we need to prove a lower bound that it is like 1 minus some small epsilon. We are almost there. It's like 1 by 1 plus something. So if we can show that this object is small, then it would be good. Then we have shown that probability nk bigger than 0 is close to 1. So this is our goal, to show that variance of nk is of smaller order than expectation nk square. Suitably small.
So one question.
Yeah.
Uh, so
Okay.
whenever we say smaller order anything, so we are always assuming that n is the one which is getting large, not r or x.
N
Okay.
is the one which is getting wrong. That's a good point. In fact, I think the calculations that we'll do will go through only for slowly growing R. So probably you can take R to be something like log of n, but not faster than that.
Okay.
But for simplicity, I'm only focusing on R fixed.
Thank you.
Okay, so we have to basically estimate the other moments. So this I will leave as an exercise. So because you have this decomposition into indicators, using that you can do computation. Uh, so I'll write this as a proposition. But I will not do the proof in the interest of time, but you can try to do it on your own. So recall that theta is this n minus s choose r minus s over n choose r. So s factorial actually r is plus 1. And we have the notation. The m is the total number of supercoupons in 2 years. So then you can show that expectation of nk power d, any dth moment, is at least d factorial times n choose d times 1 minus d theta to the power k, and at most d factorial times n choose d times 1 minus d theta plus a correction term plus d choose to psi to the power k plus something smaller order d minus 1. What is psi? So psi is uh, okay. Psi I will not specify, but okay, I'll just say psi is psi has an explicit form. Psi is r to the power r n to the power minus s minus 2 divided by max r minus 2s comma 0 max of these two factorial. And because of this particular dependence in psi, I cannot let r grow too fast in this argument. You can only take r to be like something like small, slowly growing with respect. But anyway, for our purpose, psi is going to be small. So psi, if r is a constant, then psi is of the order of theta power s n to the power minus s minus 2. So it is of smaller order than theta itself. So essentially, this is the order of magnitude of expectation of nk to the power nk to the power t. The proof will be an exercise. Just write it down as a you know, so this is basically this power t. Just introduce. I mean, break it down into a multilinear sum, right? So something like this: I is to k and I is dk, where S1 you sum over all these supercoupons. And then take an expectation, then you have to compute these expectations that simultaneously these supercoupons have not been collected by time k. They have not been collected by time k simultaneously. Previously, we just did one we just did it for one supercoupon. The probability that one particular supercoupon was not collected up to time. Here you have to do it for simultaneously for S1 up to SD. And of course, there may be repetitions here. So S1 may be equal to S2. So you have to sort of take care of all those numbers. But if you do it and carefully treat the carefully handle the terms, you get this sort of an asymptote. So okay, so I'll just be content with that, and let's try to finish the proof of this lower bound using that. So using this result, is for d equal to 2. So for d equal to 2, we have expectation of nk squared. So we can show that. Just plug this in, and this is a straightforward calculation. I've gone to explicitly. We can show that variance of nk over expectation of nk squared, nk expectation of nk whole square. This is order of 1 over m times 1 minus theta power. So just plug these expressions in, and then you can show that variance of nk over expectation of nk square is of this order. So basically, we now have to sort of plug this in this bound. So what I'll do is a further simplification. So you see, this nk, these are sort of increasing run of variables. So you see, nk is the number of super coupons that you have not collected by time k. So of course, nk plus 1 will be less than or equal to nk. In the next round, you are probably going to collect one of the uncollected ones, so it can only decrease. So therefore, this sum. So here we had this approximation here. Write it as expectation of t. Okay, so only the last term is we just need to control the last term. So these are initially they are more closer to one than later stages. So we can just use this form. So this is at least m times probability in the last one. Maybe the nm bigger than 0. So if you can show that this has the right order of magnitude, would be good. So let's do that. So we'll choose m here, m to be. If you choose m to be exactly that m that we choose earlier, it will not give you the right thing. You can try it. We have to take m to be slightly smaller. So we'll take m to be. So previously, you see, we took m to be something like this for the upper bound. If you take this, then the lower bound will not give you the right answer. So what we'll do is we'll take something which is slightly smaller, something like this. Okay? Where delta n, if delta n was 0, I have the previous choice that I used in the upper bound. So delta n will slowly grow to 0. I mean, you can use this bound here. It doesn't work if you put delta n equal to 0 exactly. So the catch is we have to take delta n to 0 suitably slow. Okay, with that aim, let us plug in our variance bound that we had here. So uh, this is your variance bound. So this is bigger than or equal to m times 1 by 1 plus variance of nm, right? Expectation. Okay. And this is basically big O of this. So this is at least m times 1 plus big O of 1 by 1 m times. Okay. So the point is we have to sort of show that this guy is small. This guy is only small if you take him to be like that. So let us see whether that is the case or not. So let us compute this object m 1 minus theta power m. So what was m? M was basically n to the power s, right? Of the order of n to the power s. 1 minus theta was like 1 minus s factorial r to s by into the s, plus some correction here. And to the power this m. This m is this guy. 1 by s minus 1 factorial times r to s times delta times n to the power s. Yeah, this big ugly looking term. So what do you get if you simplify? So n power s times, this is going to be exponential s minus
That is factorial into times delta n by n.
right, n to the power s will get cancelled. So something like delta n times s factorial are to this, right? Okay. Let's see. Equivalent is correct. So is this correct? Did I get? So I am trying to show that this is of the order of. Uh, so this is of the order of n to the power minus is factorial r to this times delta n. Do you get that?
Yes.
So that sort of shows you that if you just took delta n to be zero, that wouldn't have worked because this n to the power s would have cancelled the other n to the power s from here, and you will be left with something which is of constant order. Okay, so you won't be able to show that this is bounded. This is like 1 minus a very small number. Won't be able to show that. For this reason, you need to actually take delta n to go to zero. Very good. So so let us plug everything together. So we get this object from here. Get that expectation of t is at least um m times 1 minus this probability. So this is like 1 by 1 plus something small, which is like 1 minus epsilon. So I'll just write it directly like O of n to the power minus s factorial r to this into delta. This is what we get at the end of this calculation. M, we know what we have chosen. M is what? M is uh, 1 over s minus 1 factorial times r to this, and you have n to the power s log n. That is the right thing. That is the thing that you want. Minus, you have this delta n and n to the power s log n times uh, times this probability 1 minus o of n to the power minus s factorial r. Okay. So yeah, I mean this with this one I am fine. I mean that's the thing that I want. I just have to show that the remainder term is going to zero. See, I mean, if I take this term and multiply it with 1, that term is exactly n to the power s log n into 1 plus little o of 1. Why is that? Because delta n is going to 0. So I'll choose delta n as the delta n goes to 0 with n. So anyway, so if you take this part out, you get the main term, which is what we want. What we have to do is show that this last term is small. Okay. So what is the last term?
The last one is also like 1 plus little o of 1.
The
I
last
mean,
term should be little o of 1, right? Yeah,
yeah,
well, I
I'm talking about
mean,
the second factor. Yeah.
yeah, the second factor, yes. So what delta n should we take? That's my question. So this will get killed by this, right? You have to sort of kill this n to the power s log n using this second factor. This should give you something small, correct?
So one small o of 1 by s factorial arches.
Small o
1 by s factorial arches.
That is too small. That is too big to. It's yeah. If you want to get that is too difficult to get. I would just be content with showing that this is like n to the minus s. The main term is n to the power. I mean n to the power s. So the main term is like n to the power s log n. I just want to show that this is like n to the power s. You see, delta n can have you have to choose delta n in a suitable way. Okay, so if you choose delta n to be from here, if you choose delta n to be something like log n over let's see s factorial r to the s times log n, then I claim that I will get O of n to the power s.
I think the second term should be like n to the power s times log n. Give n to the power s log n on top, maybe.
Yeah, so times what would we get? Uh, I think I will get log something like that. Okay. I see what you mean. So n to the power s log n times yeah n to the power minus s factorial r to this delta n. So yeah, so that was a typo there. So this is like n to the power s minus s factorial r to this delta n times log n. Okay, so the point is, you see, so you already have n to the power s times log n. I sort of want to kill off this log n using this extra delta n. I want to sort of kill off this extra factor of log n. If I take delta n to be something like this, then this will get. You cannot take delta n to be too small, otherwise you'll mess up the other terms. So I'm too fast going to zero. So that's it. So that sort of tells you that this is like into the power is like minus 1 trillion times r to this. So that gives you the lower bound, and yeah, we get matching upper and lower bound, so that proves that expectation of t is into the power is log n. So by the way, so how long does this talk usually go? 1 hour or more than 1 hour?
Usually it's 1.5 hours.
1.5 hours. So I have some more time, right? Okay, so this proves that expectation of t is into the s log n by s minus 1 factorial times factorial, which is like n to the power which is exactly into this log into this. And let me know if you have any questions.
This
Okay,
is almost
so
exactly like the coupon collector problem, just uh,
yeah, it's exactly
on
the
different coupon.
right. But the proof is much more complicated because of this constraint that you have here. That the super coupons that you collect in each round, their union is a R subset. So they are not any arbitrary super coupons. They come in a structured way. And incidentally, this also gives a more roundabout way of proving that for the usual coupon collector problem, you get into n log n over r this type of assembly because this is a more general version. Okay, so how about a distributional result? So can we say something about here we just show that on an average expectation t behaves like this. So we can show that T has a limiting Gumbel distribution. This is also the proof technique is also interesting in its own right. So I'll discuss a little bit of that. So so if you take T, we know what is the first order behavior, like the expectation of T. That behaves like this. So I'll subtract that from T. T minus n to this log into this over R to this. So if you scale it by into this divided by R to this, to ensure that this converges in distribution to a standard Gumbel distribution. What is the Gumbel distribution? It's a random variable x follows Gumbel if its CDF is given by this. So since we have already taken the trouble to compute or at least estimate these moments, all of the moments, you can guess that one way of attacking this would be to use moment method. So let's try to use it. So let us call this random variable z of n. We are interested in showing that probability zn less than or equal to x converges to e power minus x. Need to show this. So let us write everything in terms of my random variable, uh, those count random variables that we had earlier in case. Okay, and then if nk is a count random variable, if we can sort of find a limit theorem for nk, we can use that to uh, prove or get the distributional limit of this z. So what is this? So this is probability t minus the mean, which is into this log to this over r to this. Less than or equal to x. So we can write this as probability t is less than or equal to something. But this k is going to be, yeah, this times x plus that. So basically x plus log into this times this by So we have at least that. So yeah, so if t is less than or equal to k, what can I say about nk?
Okay, 0.
Nk is 0, right? Nk is 0. Very good. So we want to show that probability nk equal to 0 converges to e power minus x. Now that sort of gives you a clue what should be happening. What would be a sufficient, what would be a guess? If nk converges to some distribution, we should have this. What would that distribution?
Sorry, e to the power
Can
minus
you
x.
repeat the question?
Yeah, the question is if we can show that nk is a discrete random variable, non-negative integer valued random variable, right? So if you can show that nk converges in distribution to some known distribution, then we can hopefully get this. Now, as someone just said, if you can show that this converges to a Poisson distribution with parameter e power minus x, that would imply that probability nk equal to 0 converges to probability that a Poisson random variable with mean e power minus x is 0. That is exactly e power minus x. So therefore, it is enough to show that nk converges in distribution to Poisson e power minus x. The point is k is not something fixed. You see, k is also changing with n, growing with n. So, so here is a proposition. Nk does converge in distribution to Poisson with parameter e power minus. Where k is this one. Yes. How do you prove it? Well, using moment method. So what you can show. So again, I mean, I will not do it. You can try to do it. It's a good exercise. Uh, Proof. We show that expectation of nk to the power d for any d. And what is to expectation of n power d follows. This is true for all d. Convergence in distribution is in this case equivalent to convergence of all the numbers. So if you can show this
This would follow from the previous proposition you made.
from the previous
So,
proposition, that yes, that's so since nk can be written as the sum of indicators, uh, so I'll give you a heuristic idea. And how do you guess that it would be Poisson, right? So what is nk? Nk is, remember, the number of supercoupons we haven't collected by time k. So it was this indicator ISK, where S is you sum over all supercoupons, right? This is nk. The problem here is that these ISK, these indicators, they are dependent, they are correlated among themselves. So uh, let's say, suppose they are not correlated, okay? Suppose they were all independent indicators. In that case, we can very easily show that. So this is like a binomial distributed random variable, right? If they are all independent random variables. So if you pretend that uh, these ISKs are independent, they are not in this problem, but pretend that they're independent. In that case, what do we get? This is a binomially distributed random variable. What are the parameters? So ISKs are Bernoullis, right?
Yes.
And what is the parameter? It is 1 minus theta to the power k. That's what you have shown earlier.
Yeah.
So this is binomial m 1 minus theta power k, right? Uh, it turns out that this here you get a Poisson approximation with this type of k. This converges to Poisson power minus x. If you take a, you know what m is? M is like n choose s. Theta, you know, is s factorial by r choose s times r choose s by n power s into 1 plus little of 1. And k we know is this x plus log n choose s divided by not divided by times n choose s by r choose. So by Poisson approximation to binomial, when does that happen? If you know that m times 1 minus theta power k, the number of tosses times the probability that goes to a constant. In that case, we have a Poisson approximation to a binomial,
Minus.
right? So it is enough to show that if this happens, then this convergence happens here. This convergence happens. Okay, you can quickly check that this is indeed the case. If I take these as my parameters, then m times 1 minus theta power k would actually go to e to the power minus x. So that is kind of the idea. I mean, why would you expect a Poisson minus existing? Well, these are not independent, but they are not also very highly correlated. They are weakly correlated. If you compute the covariance, you'll see that they are weakly correlated. So although this is not binomial, because these indicators are weakly correlated, you can still show that the moments converge to the corresponding Poisson. So this is kind of the heuristic behind why you should expect Poisson limit for India. Okay. So these I mean you can I think Vikram already linked to the paper. You can check that. It would be a good idea to try this as an exercise. Show that this is true, even if you don't have independence. Okay. In the final 15 minutes, I will talk about a more general version. So I'll view this coupon collector problem in a different way. So basically, what is happening, you have this space of n choose s many super coupons, right? So what are we doing here? So at each round, we are collecting some r choose s many super coupons. And we are doing it in an independent way. So each round we sample with sample R coupons without replacement and mark all the super coupons and collect. But the rounds themselves are all independent. What if we have some kind of a process where the rounds are not independent? There is some kind of Markov dependence. I want to talk about a problem like that in the remaining 15 minutes. Uh, okay. Ourselves, not supercoupons. So previously, what were we doing? At each round, we are selecting one R subset at random, right? So the R subset you draw at time t is independent of the R subset you draw at time t plus one. So it's kind of simple. But What if we introduce a dependence? Okay, so let us denote by HT the R subset drawn at round T. So at time t plus 1, I will not draw another independent R subset. What I will do is I will just take HT and replace one of the coupons there by something selected at random from the rest of the group. Okay. So yeah, how do I write it? It's HT minus X union Y, okay, where X is uniform on HT and Y uniform on HT component. Is this clear? So at time t plus 1, I see what I drew at round t. I take one of the coupons in that bag at random and replaced it with another random coupon drawn from outside HT. So this is how you get HT plus 1 from HT. The rest of the process is as before. So uh, you get this HT, you mark all the super coupons, that is S subsets, as collected. But instead of the previous independent dynamics, we now have a Markovian dynamics. So there is genuine temporal dependence. Again, I ask the question, what can we say about T, the time to collect all super. So unfortunately, we don't know the answer. So we have a conjecture based on simulations. I'll write down the conjecture. The expectation of T in this case, our conjecture is that, so I'll write TRW here. So there is a connection between this process and a particular random walk, at least in the R equal to S case. But I'll denote this time by RW, TRW. So the conjecture is expectation of TRW. See, the problem is previously I was at each round I was drawing independent R subsets, right? And we just showed that the time to collect all the super coupons uh, is of this order. Now, if you have this Markovian dependence between the R subsets that you draw, what do you expect? Would this be bigger than the previous one, or smaller than the previous one? That is the previous process. Previously, these HTs were all
Basically,
independent.
larger.
They will be larger, right? That's
Yeah.
natural to expect because you are seeing less number of new coupons potentially because you are not changing the HTY much, right? Yeah. So correct. So we expect the TRW to be larger than previously. Okay, larger by what amount? Our conjecture is it's R by S times expectation of T, the previous one. I mean, okay, our conjecture is not this. Our conjecture is slightly weaker. So this is R by S times N choose S log N choose S by R. It's slightly weaker. So our conjecture is expectation of T RW over expectation of T. That is like R by S times 1 plus little r. Now you might wonder, where do I get this R by S factor from? Well, again, the heuristic guess is that if if you did not have any dependence, then at each round, how many new coupons I am collecting? I'm collecting R choose as many new coupons, R choose as many distinct coupons at each round, right? Distinct from the previous round potential. What about this new process? How many new coupons am I collecting? If I have a uh, if I have this Markovian dynamics, yes. See, I have only changed one of the coupons, right? I have only introduced one coupon here.
It should be
So
R minus 1 choose S minus 1.
exactly. The so whatever you collected at round t plus one, you get R minus one choose S minus one new coupons. But in the previous model, there is a chance that you would see a completely different R subset. There is a non-trivial chance that would happen. In fact, a very large chance. You can calculate the probability. So this R by S is coming from the ratio of these two. That's the amount of slowdown you expect. Because you in this new model, you are saying basically R minus 1 choose S, R minus 1 choose S minus 1 by R choose S, this fraction fewer coupons. So we expect that this is the right behavior. This is a conjecture.
So ratio is, I guess, the other way around.
Sorry,
So should it be S by R, the the last thing that you do?
this one.
Yeah.
Yeah, this would be S by R. It's P word, right? So yeah, S by R. So since you are seeing fewer new coupons in the second model, on an average, it should take more time to collect all. Okay. Uh, so that's the conjecture. So far, our simulations show a remarkable agreement. Uh, we believe that this is true. We can prove that this conjecture in the case R equal to S, and there is a connection with random walk. So in the remaining 5 minutes, I will try to sketch that connection. So, okay, when R is equal to S, there is no slowdown because you are seeing one new coupon in both the models. So there is no slowdown. So when R equal to S, yeah, this is a theorem. Expectation of TRW or expectation of T 1 plus 2. Okay, so what is the connection? Why am I writing RW? What is the random walk? Well, this is a random walk on the on the space of all possible R subsets. Okay? So this Markovian process is equivalent to a random walk on the following graph. What is my graph?
Set up our subset.
Exactly.
Sorry.
So V is the set of all R subsets. And you see what the dynamics is. I am picking one from the R subset and replacing with something from the outside, right? So you can guess what the edges of this graph would be. An R subset is connected to another R subset if, when are they connected?
Only one element is there.
So their intersection, what can you say about the size of their intersection? Exactly. It took R minus 1, right? They only differ by one element. So this is a graph that you can define on the space of all R subsets, and this process is exactly a random walk on that graph. Okay. Now, what is TRW here? Can we relate it to something about the random walk? TRW
Cover
is the
time.
time when you have collected all the super coupons, right? So, what can you say about this in the random walk language?
So just the cover time of the graph.
Exactly. So, I have covered all the vertices, right? The TRW is basically the cover time of this random. Technically, it's TRW minus 1 because the starting thing in our process is also random. But anyway, so TRW minus 1 is actually the cover time of this random. So since we can refresh this process as a random walk, now we can use random walk techniques to compute expectation of TRW. It turns out that, so I don't know how much random walk you have seen, but for uh, complete random or random walks on connected graph, there is a very beautiful theorem due to Matthews, which gives an expression of the cover time in terms of the hitting times of states. Okay, so I'll write it down here. Suppose you have a random walk on a graph. Okay, so then the cover time. The cover time. I'll call this the cover time, the expected time to see all the vertices, and I will denote it by T cov. And if the starting vertex is phi, then the Matthews theorem shows that uh, the cover time is this harmonic number. So here V is the number of vertices in your graph times the maximum hitting time of two states. What is HUV? Uh, Expected time to hit vertex V uh, for a random walk started at. This is the hitting time of V started of the random walk started at. Okay, this, and you have a lower bound which is in terms of the minimum hitting time. Okay. So so we have this very beautiful result due to Matthews, and we can use this uh, in this setup to compute expectation of TRW explicitly. See, how many vertices do I have in my graph? I have n choose r many vertices, right? So you know what this time. So and what about, so basically the job is to find out these HUVs. if you can estimate this HUVs, would be good. We can just apply this theorem. It turns out that this graph is, as you can see, I mean, I have just put all possible R subset and connected them. They differ at one coupon only, right? That's a very symmetric graph. You can see that it's a deregular graph for some D. And you have a very nice structure. I mean, so you can show that. So I'll write this as an exercise. This graph is very symmetric. It has a very nice automorphism. It has very nice automorphism, using which you can show that HUV only depends on the size of the intersection of U and V. So what do I mean by it has nice automorphisms? Well, if you take two vertices UV, such that U intersection V is, let's say, 4 vertices, right? Then there, using an automorphism, you can map U to U prime and V to V prime. So it has very simple, very nice symmetries. So therefore, the heating time only depends on U intersection V. And the U is a R subset, so there are only a bunch of possible values, right? It's up to 0 to, 0 to R at most. So there are only at most R plus 1 many HUVs. Now, I think you have seen this in when you dealt with random walks, that if you, so this is like a hitting time. So started at U, the random walk wants to visit V for the first time. Right? So a typical way of analyzing random walks is to see what happens at the first step. If I just see what happens at the first step, let's say it goes from U to some other neighboring vertex W, right? So that happens with some probability. What is the probability? Du with probability 1 over du, it goes to some other vertex W. And then from W, the random walk restarts and it has to hit V again, right? So if you take an expectation, you should get something like this, right? So for random walk on one graph, you have this very nice hitting time equation. If you are familiar with harmonic functions, you'd be immediately on board. This is like an average of the sitting time.
Yes.
As the average of hitting times from the neighboring states. The point is, these are all linear equations, and there are only a bunch, I mean, if we didn't have this symmetry, we would be in trouble because there are lots of variables here. Like HUV is a quadratic number of variables in the number of vertices potentially. But because of the symmetry structure, there are only R distinct variables here, HUVs, R distinct HUVs for these linear equations. So you can explicitly solve this linear system of equations. And from that, if you apply Matthews theorem, you can show that this cover time, which is the same as expectation of TRW up to this constant, relative constant 1, is exactly what we want, which is this n choose R, n choose S log n choose S by R. Okay, so I think it's already 9:05, so I would like to stop here. Let me know if you have any questions.
So from that, do we get only one side of the boundary?
No, we get both sides because so this is true for all. This is true for any graph, any random walk on any graph. So if you can calculate HUV explicitly, for all these intersection sizes 0 to R, we can actually show that these two are of the same order. The max of these numbers and the mean of these numbers are actually of the same order. So this Matthews theorem actually gives you the the exact order of magnitude. So solve these linear equations. In at most r plus 1 variables. I mean, you don't have to solve it explicitly. You just need to find out the order of magnitudes of these numbers. You can show that the mean of these numbers is the same order as the is of the same order as the max of these numbers. So therefore, Matthew's theorem actually gives you a tight estimate. So this is a very beautiful theorem. So a good reference for this would be this book by Levin Perez and Wilmer on Markov chain and mixing times.
So we can talk about the expectation of this. Are there any conjectures about the convergence or other moments?
We don't have any conjecture because uh, you know doing this simulation is quite difficult because we have to do a random walk on a very complicated set. Like you have to sort of look at this graph, right? You have into this many things that is quite big. So we could do the simulations only for r equal to r equal to 10 and s equal to 2, something like that. And yeah, to answer your question, we don't have any conjecture about the second moment. Even the first moment is not known for r not equal to s.
Even for the say r equal to s situation, then do we have?
The second moment for r equal to s, yeah. No, we don't know.
Okay. And also these convergences, particularly the first one, like are there any other things to influence in the moment? Say we know the expectations, the variance or the third moment or something like that.
We know all the moments, right? Because we have this estimate. Oh, you mean for TK?
Yeah, yeah, yeah.
For TK, you can do it using NK, right? So I think you can compute it. If you are interested, you can try to compute it.
Okay.
So yeah, the idea is, if you want to calculate probability, let's say TK power D, right? Something like that. Then write it like sum of probability T power D bigger than 0, T power D bigger than K, which is same as probability T bigger than K power 1 over D. And then this is probability n K power 1 over D bigger than 0. Right? So we can get a handle on this using this n case.
Got it.
It would be more cumbersome, I guess, but I guess it can be done. Oh, by the another thing I did not mention here, which yeah, also for this model, it's not known, but you can also try to look at. So instead of trying to collect all the super coupons, suppose I want to know what time do we take to collect, let's say 50% of all the super coupons. So you can define T alpha to be the time it takes to, let's say 1 minus alpha percent of all super coupons. Instead of collecting all the super coupons. But alpha is like something between 1 and 6. And then you can again show that expectation of T alpha. This is also quite interesting. You cannot do it using just the first and second moment method. You have to use all the moments simultaneously. So you can refer to the paper for the proof. But the answer is this is like uh, check. I think log of 1 over alpha times, yeah, n choose s by r choose s log of. And again, it's our conjecture that T alpha in this case suitably normalized. You have to subtract the mean. Yes, the root of it actually converts this to a standard Gaussian. The point is that the last, you see, the behavior here is like n to the power s. So for any constant fraction, the behavior is like n power s. Only the last few coupons are very difficult to collect. That's why you get that log n factor. To collect all the super coupons, you need n to the power s log n up to some constant, right? That's the behavior. But to collect any arbitrary, say 99.99% of all the super coupons, for that you still need n to the power s time or order of n to the power s time. Only the last few remaining coupons are really difficult to find. They actually give you these extra log n factor.
Sir, what is the paper you referred?
uh, about the paper you post, link to in the abstract.
No, this one. This TL.
Oh, this is there. This is there in that paper. I did not have the time to discuss it here, but it's there. Its proof is also a bit interesting because you need all the moments simultaneously to prove this.
Okay. Are there any more questions? Okay,
But
if
if
there
you are
is no
able to
question,
do some simulations or come up with conjecture, that would be you are welcome to do so. That would be very helpful. Yeah, I mean, there are a bunch of conjectures in the paper. You can also try to prove those. Some of them. These problems are very easy to state, and most often they are proved by some clever application of these moment methods. So the techniques are all very elementary and accessible.
yeah, it is accessible to everyone, I think. Now, okay, if there is no questions, let's wrap up. Thank you, sir,
Yeah,
for
thank
coming
you for
here.
having me. I hope you like the.
Yeah, everything is too simple to see here, and I liked it pretty much.
Yeah, thank you.
Thank you, sir.
Yeah, I would like to go back to seeing the World Cup. So, yeah,
Okay, thank you everyone for joining us. Let's wrap up now. Thank you, sir.